Quadratic function. Key features of a quadratic function. Does anybody remember what a quadratic function is?
Function with 4 terms.
No.
Two degree.
It's a degree 2 polynomial. Degree 2 polynomial is a quadratic. So we're going to be looking specifically today at the quadratic parent function. The quadratic parent function. It looks like this. F of x equals x squared. Notice we've got function notation again. F of x equals, and we're looking at x to the second power. Right, this is the simplest function in the quadratic function family. And again, all quadratic means is that it is degree 2. This is the simplest degree 2 polynomial I can have. All right, so what we're going to do is we're going to figure out what the graph of a quadratic function looks like. So far, the only thing we have graphed has been linear. Y equals mx plus b, right? F of x equals m times x plus b. Remember, a linear function is degree 1. What's the exponent of x in a y equals mx plus b form? 1. Right? There is no exponent for x. So there's an understood 1 there. Well, now we're looking when x has a degree 2. Or a second power exponent. So we're going to make a rough sketch of the graph together. And then we're going to put in our graphing calculators to see what it looks like. So if I didn't know what this looked like, I'm going to plug in some values for x and find out what their y value is, which we're going to call that the f of x. So what are some x values you would want to plug into this function? 0. That's a great thing to plug in. What else would you like to plug in? 1. That's a great number to plug in. What else would you like to plug in?
4.
No. 2.
3.
That's a great number to plug in. 3, that's too big.
Oh. 2.1?
You want to plug in decimals?
No.
I don't either.
1, 2, 3, 0, 1, 2, 3.
3's too big.
Why are we doing too big?
-1.
-1. That's a great number to plug in. Let's see what it looks like.
-2.
-2. That's a great number to plug in. To see what it looks like.
3's too big.
-3's too big. Let's plug in 3. Just for fun.
-3?
No, I'm not plugging in -3.
Too big.
Yep, too big. So if I plug -2 in for x, what is the output? Right, these are my inputs. I can choose any inputs I want. So if I input a -2, and I know I've got to write everything out because I've seen what you guys do. This would be f of -2, which we can write that as -2 squared. I'm plugging in -2 for x. So what is -2 squared? So guess, in our heads, a negative times a negative is a positive. 2 to the second means I'm multiplying 2 by itself. So 2 times 2 is 4. So if I plugged in a -2, I got out of 4. Now I'm going to show you how to put that in your calculator because I could tell by the looks on your faces you didn't know what -2 to the second power was. So here we go. Everybody on their calculator. You need to put a parenthesis. Does everybody see the parenthesis? You're going to click the negative button, not the subtraction button. The negative button. Everybody knows the difference. Then 2. Then close your parentheses. And then if you want to raise it to the second power, you can click the button that says x raised to the second power. It is on the left side, right above log. Does everybody have this put in their calculator? Parenthesis, -2, close parenthesis, squared. Click enter. What did you get? You see how we plugged -2 in for x. Do I need to help anybody put that in their calculator? Okay, so when I plug in -2, I get out a 4. Now let's plug in -1. So what is -1 squared?
1.
So you can put it in just like you did before. Do I need to go through the steps again? Has everybody got it?
We got it.
-1 to the second is 1. What if you plug in 0? That's going to be 0 to the second power. So what is 0 times 0?
0.
0. No such thing. Now let's plug in a 1. What is 1 to the second power? 1. Now let's plug in 2. What is 2 to the second power?
4.
4. Now let's plug in 3. What is 3 to the second power? 9. Does everybody see where I'm getting these values from? Just plugging in. I picked the x's. I found the y's. Now let's put these points on a graph. So where is the point -2, 4? Well, that means from the origin, -2 means I'm going left 2. +4 means I'm going up 4. So the point -2, 4 is happening right here on my graph. Okay, what's the next ordered pair that I have found? -1, 1, which means from the origin, I'm going to go -1, which is left 1, +1, which is up 1. Am I going too fast?
No.
I really need you guys to start speaking up because I saw your factoring again. It's like I didn't show you guys one thing for 3 weeks. So I'm going to go to the next point. The next point is 0, 0. That is the origin. This is that point. The next ordered pair is the ordered pair 1, 1, which means I'm going to go right 1, up 1. The next ordered pair is 2, 4. So from here I'm going to go right 2, up 4. What are you guys noticing here? It is kind of like a reflection of itself.
Yeah.
Right? It's the same thing happening. Now look, where would my next point be? It would be at 3, 9. So this thing grows pretty quickly. And then think, the next one would be 4 and what's 4 to the second? 16.
Oh.
Said that was like exponential or something like that?
Yes, because it's got an exponent. That's called exponential growth, where it grows very quickly. This graph looks like, no, a U.
A V.
There is another graph that is a U, or there is another graph that is a V. That's why I'm very specific. These are curves. These are not a straight line and another straight line. That makes the V. We'll look at that later. But this is a U. Does anybody know the shape of this graph? This is not linear. This has another name. Well, it is a quadratic function. So linear functions look like lines, right?
Is it something like bilinear or something?
So this is a quadratic function. And quadratic functions have a shape. So the shape of this function is called a parabola. Parabola. That's the U-shaped curve. A parabola.
That's gonna be every time we have a quadratic function like this.
So like,
If you ever have x to the second as your highest degree term, the shape is going to be a parabola. Even if it has multiple terms, right? We can have a trinomial that has 3 terms. But if it's a quadratic trinomial that's in the form of ax squared plus bx plus c, this is a quadratic trinomial, its shape is still going to be a parabola. What? Somebody else was asking something else.
it was me. But I forgot.
Okay.
No. So like, how are we gonna do factoring with this stuff?
Well, we're not factoring yet because this is the most basic form. But eventually we're going to get things that look like this. And we're going to need to make the graph. And we'll get there when we get there. We're not there yet. You're going to have to factor it. But, well, we're going to factor it to find x-intercepts. It's a very specific thing. But we're not there yet. We'll get there. Questions so far about the shape, the name, okay? Some more things I need to talk about. These parabolas, they have 2 options. They can either open up like a U. Any questions here about opening up or opening down? Okay? Another key feature that is on every parabola is going to either be its maximum point or its minimum point. You see how when it opens up, I have a minimum, that is the lowest point it reaches, or if it opens down, there is a maximum. That is the highest point it reaches. Does anybody know what the name for this point is that's the highest or the lowest? Besides maximum or minimum? It's okay if you don't. That is the vertex. When something reaches its vertex, it's reaching its highest point or its lowest point. Okay, and then the last thing we need to talk about with a parabola is, remember how y'all said it kind of had, it was like a reflection? I think it's how you said it. On one side of the y-axis. So if you look at, so this is like your line of symmetry, but it has a different name. Okay? This line that cuts right down the middle, this is called the axis of symmetry. It's just like what you think of as a line of symmetry. But it's an axis, like your x and y axis. It's a line that cuts right down the middle of the parabola. Cuts it into 2 equal pieces. Yeah. Now, a couple of things I want to add here that I didn't think of in the last class. The vertex is just some point, right? It's going to be some point that is the lowest value or the highest value. So we call that point h, k. H is the x value, k is the y value of the vertex. So in our previous example, the vertex was 0, 0. Right? It was the origin. It's just some ordered pair. Now, when we talk about the axis of symmetry, we're going to give the equation of a vertical line. So when we do that, it's always going to be x equals some number as our equation of a vertical line. So in our previous example, the axis of symmetry was at x equals 0. So what you have done by putting a negative in front of the x squared is you have changed the leading coefficient. You guys remember when we talked about leading coefficients? The first term, if I had negative 2x squared plus 3x plus 8, this is a quadratic. What is its leading coefficient? The leading coefficient.
Oh, 8.
Okay. Coefficient. Y'all need to write this down. Coefficient is only the number. Coefficient never has a variable. Never has an exponent. The leading coefficient is the number that's in front of the highest degree term. So here, what is my highest degreed term? X to the second is the term. Negative 2x to the second, which means the leading coefficient is negative 2. Is everybody good with this? So for a quadratic, your leading coefficient is called a, because it's in the form of ax squared plus bx plus c. Well, we're not doing that, but I'm just saying the number in front of the x squared term is my leading coefficient that starts with an a. So what they're talking about here is this a for ax squared. How does this a out front affect the graph? So let's plug in some different a's to see what happens. So let's go back and click y equals again. Now go down to your second equation. Don't overwrite the x squared. Leave it in there. Go down to the next one. What do y'all want to change a to? Let's all change it to the same thing. 2. I like it. So let's put in our calculators 2x squared. And let's graph it.
They come with tighter in.
We call that a stretch, right? So your graph, here is your original x to the second. If I multiplied it by 2, it's going to be taller and more narrow. It's like I took the blue graph, it's pinned down at its vertex, and I stretched it. Think about those stretch toys you used to have. What happens when you stretch it? It gets taller and skinnier. That's what's happening here. All right? Does everybody see what's happening? Now, what do you think is going to happen if you put in a 3?
It's going to become an even more stretch.
Even taller and even more narrow. Let's do it just to confirm. Go back to your y equals. And now go down to the third one. And put in 3x to the second. And graph. See what's going on? Even tighter and taller. Any questions?
Why is it that 1 and 2 are more farther apart than 2 and 3? Like when you put 3x squared in there, it's like literally right beside 2x squared. And then why is it that 1x squared?
Because it's exponential growth, it's not proportional. We're no longer dealing with lines that are proportional and work in the same accord. And if you zoomed out and went up some on your graph, it might be more dramatic the higher numbers you look at. But again, I wouldn't focus on that too much right now. Okay? Now, how can I make let me ask you this. How do you think I can make the graph look more like a Coots? Right now, you are making this taller and skinnier. Cootses are short and wide.
Isn't that negative?
You see me? No. It's not a negative number. So how can I take my original and stretch it this direction? We call it a compression. Think
Oh.
about I'm getting on top and I'm squeezing
Would you
down.
have a bigger power?
Nope. It's still got to be a quadratic, so it still has to be x to the second.
Add.
No.
Smaller,
How did I make it taller and more narrow?
Bigger number.
I multiplied by 2 and 3 and
Bigger
4 and
coefficient.
5.
So you divide.
You could go that route, but I still want to multiply. Because if I start putting division in there, it no longer looks like ax squared plus bx plus c. So what could I multiply by that is making something smaller? It's like dividing. What's another way we can divide by 2?
A fraction?
Ah, never mind.
Another way we can divide by 2 is multiplying by a half. Or multiplying by a decimal. So let's go back to our y equals. And let's go to the fourth line. And let's put in 0.5 x to the second. I've now put in a decimal number that's less than 1. Multiply it by something less than 1 and graph it.
That's a big goal.
Now what's happening to my graph here? It is becoming compressed. Think about taking the graph and squishing it together. It's getting shorter and wider. Okay, so the question here is, how does A affect the graph? Well, if the A value is bigger than 1, so when we put in 2 and 3, what happened to the graph?
About taller and skinnier.
So we stretched the graph. And again, by stretch, it looked taller and skinnier. That's what we mean by stretching.
Okay, so while you was going over that, I like play around with it a little bit, and the smaller the decimal, like if you go to the hundreds place, thousand place, it starts to become more of a straight line. When does it finally
It
become a
looks more like a straight
straight
line.
But it's not though. It's still
But
like
it's
a curve.
not.
Gonna become a-
It has to be 0.
Yeah.
Because if my A term is 0, what happens to x squared? What is 0 times x squared? 0.
Yeah.
And now what are you in the form of?
5 million.
Or bx plus c.
This is linear.
Yeah.
This is mx plus b.
Oh.
It's x to the first power.
I got you.
Because I've lost
That ax squared.
the x squared term.
Yeah.
So those are not called quadratic anymore. We'd be going back to linear.
So like, you can go to like, what should I say? So like, when I went to the let me see, I did 0.005, so that's what like the thousandth place almost.
Mm-hmm.
So like, what would be after that? Like the millionth place.
Mm-hmm.
So would
10
it-
thousandths.
Yeah, 10,000s. Would it just keep on getting flatter and flatter and then like being raw on the line?
It's gonna look more linear. Uh-huh. Okay, now what happened when my A value was between 0 and 1? That's what this says. A is bigger than 0, but A is less than 1. So when A was between 0 and 1, what did that do to the graph? So the word that we use is it compressed the graph. Again, I always say that made it look like me. You made it shorter and wider. Squish the graph. Okay? That's what's happened. So at the beginning, everything we put in for A has been positive. We pick between 0 and 1, and then we pick things bigger than 1. All right, well, what happens if I make the A negative? So in our graphing calculator, click Y equals. Let's clear out everything except the first one. Let's keep x squared.
Oh my gosh.
Make it
Let's
like a
keep
negative
x squared.
Erase everything else.
Erase everything except x squared. Is everybody good?
two. Hold on.
Okay. Okay, so now in the second one, let's put in negative x squared. So again, make sure you click the negative button, not the subtract button. Why did you put 2? I knew it. Well, you can.
It just reflect over the y-axis there.
It is a reflection over the x-axis, not the y-axis.
Wait, oh yeah, x is going.
This is the x-axis. We reflected over the x-axis.
Yeah.
Does everybody see that when it was a negative number? So what do you guys think negative 2x squared will do before you put it in there?
Skinnier.
So the negative is going to reflect it. The 2 is going to stretch it. Right? But it's going to be stretching downward now. Put it in your calculator. Put in, beneath it, put in negative 2x squared. So yes, if the A term is negative, what happens to the graph? If A is negative,
It becomes a highest peak. Wait. It has a highest peak now. And
it has a maximum.
Yeah, maximum.
So what can we say about the graph? We could say it opens down. When A is positive, the graph opens up. When A is negative, the graph opens down. So if A is positive, the graph opens up. If A is negative, the graph opens down. And then the actual number still does the stretching or compressing like it did if it was positive. So if I put in negative 0.5 x squared, what's that graph going to do? Well, the negative means it's going to open down. The 0.5 is going to do what? It's going to compress the graph because it's between 0 and 1. Right? So negative reflects, 0.5 compresses for those A terms. So now, let's just look through these 4 examples of a parent function being transformed. And let's tell, how does the graph compare to the parent function? So what I'm looking for, really you only know a couple of things right now.
That A when positive.
So when I look at 5, first thing I want to know, does it open up or down? How do you know?
A is positive.
Because it's positive. It's positive, it opens up. Now the 4, what did that do to the graph compared to the parent function of x squared? It would have stretched the graph. It would be taller and more narrow. That would be a stretch and it would open up. Okay, 6.8 x squared. Would it open up or down?
Nope. Well, open up, yeah. Open up.
It opens up. How do you know?
Because it's positive.
Because it's a positive A value. A is positive, it opens up. The 0.8 does what to the parent function?
Make it wider.
It's going to compress it, is the word we use. We use stretch for getting taller and skinnier, compress for getting smaller and wider. So it does stretch it outwards, but think about it in terms of the x. That way we don't have stretch for both. So we compress the graph, and it still opens up. 7, what about negative 5x squared? Does that open up or down?
Down.
Down, and we know that because it is negative. What does the 5 do to the graph?
Compress. No, shorter.
It's going to stretch the graph because it's bigger than 1. So it's going to stretch it, which makes it taller and more narrow, skinnier.
It just opens down,
It does. The negative opens down.
but it still stretches.
Yeah, the 5 still stretches. Correct. And then 8, negative 0.4x squared. Opens up or down?
Down.
Opens down. And the 0.4
Compress.
compresses the graph, which is going to make it wider and shorter.
Okay,
Well, we have not talked about increasing or decreasing yet. We have not even talked about it. I'm fixing to tell you guys.
Well, yeah, it's go, like it opens up,
It does open up.
but I think it's increasing,
Okay,
I think.
so this, in my Math 112 class, is what, when we go over this stuff, this is what they miss the most. They don't understand this part. No. So, we want to know over what interval is f of x equals 4x squared increasing. So, in our graphing calculator, I want us to go to y equals, clear everything out, and only put in 4x squared. This is what you should have.
Do you just, like, took a photo? Pretty cool.
How do you think I'd get everything up there? Take a picture.
Well, I'm saying it was pretty fast.
Thanks.
So, like, how they missing it? I don't know.
Okay, well, I have not went over the answer yet. So here's what we talk about by increasing or decreasing. If your pay increases, what's happening? It's going up. If your pay is decreasing, what's happening? It's going down. So, when it's asked over what interval, you have to think of graphs like a timeline. How do you read a timeline in a history class? Left to right. This is the same way. When I want to know if the graph is increasing or decreasing, you need to read it like a timeline, from left to right. So I'm going to write that down here. Read like a timeline. From left to right. Now, the hardest part about this with math is how far left can you go? Like, right here's where the graph stops. Like, my actual axis stops. But this graph keeps going all the way over here. So you got to think, I'm as far left as I can get.
So wait, would it just be infinity then?
But think about it. So get as far left as you can get, and then start reading from left to right. So when we first see the graph, that's happening right here. Right? We're finally seeing the graph. Reading left to right. As I'm reading from left to right, what is the graph doing?
So it's,
When I first see the graph, the y values are getting smaller. So this graph starts off decreasing because the y values are going down. Right? Think about what's happening off camera or off our picture. Way over here from left to right, as I read it, back here the y value was this high. But now here the y value is this high. What's happening to my y values? they are decreasing.
But the X's are increasing.
But we always make the x's increase. Because we always read it like a timeline.
Yeah.
From left to right.
So,
So as x is increasing, the y's are decreasing. So I could say, let me write this on here. I would say the graph started off decreasing.
How do you write that tiny with just your finger?
I've done it a bunch.
I'm trying to like process this.
Wait.
No. Just think of this graph. Quit trying to jump somewhere else. Do you understand why this is decreasing?
Yes.
From left to right, it's going down. So when did the graph start decreasing?
0, 0.
No.
I mean, at,
How far left could I get?
well, 10 on the.
How far left could I get? Forever. So when I went in the beginning, right? Let's go biblical. In the beginning, boom, wherever that's at, I can't get there. It's negative infinity. In the beginning, the graph was decreasing, and it was going down. No matter how far left I go, coming left to right, the graph's going down. So this starts decreasing at negative infinity. Way over here, because it's going down.
Oh, how's it gonna increase? Because either way it's going down.
No.
No, look when you get.
When does this stop decreasing? When did my graph stop going down?
0, 0.
When the x value is 0, the graph quit decreasing. It quit going down. So this graph was decreasing from negative infinity until 0. Because remember, we're reading it like a timeline. My answers are always x's. So from negative infinity to 0, it's decreasing. Then what happens at 0 on my graph? It starts to increase. And when does it stop increasing? It never stops. It increases forever and ever. Amen. Thank you, Randy Travis. Okay, so this is increasing. When did it start increasing? At 0, when the x value was 0. And when did it stop increasing? At positive infinity. So over what interval is it increasing from 0 to infinity? Over what interval is it decreasing from negative infinity to 0? Parabolas will always do both. And they stopped doing it at the vertex. Right? This was going down until it hit rock bottom. This is the minimum. It decreased until the minimum, and then it started increasing forever.
This is going to be real confusing, but real simple.
So when I look at this graph, and I want to know where is it increasing and where is it decreasing, I'm just going to use I and D for short. So again, I have to read this like a timeline. So I'm going as far left as I can. So all the way at negative infinity, when I first happen upon the graph, what is the graph doing? It's going up. This y values are going up. When I first see the graph walking from left to right, that blue line is getting taller and taller. It's increasing. When does it stop increasing? At 0. At an x value of 0. So I could say this graph at the beginning was increasing. So from negative infinity until 0.
So it's just.
It was increasing. Then what happened to the graph after 0? It starts going down. It started decreasing. And when did it stop decreasing? It never does. So this was decreasing from 0 to positive infinity.
So the song just different when it's down. So, okay, I got it now.
Okay, so when I look here, let's just talk about it increasing and decreasing. Don't worry about how it got there yet. I know what I'm doing. I moved it there. But think about it with increasing and decreasing. As I happen upon the graph from left to right, what is the graph doing initially? It is decreasing. So it starts off decreasing from negative infinity
To 5.
until when? When does it quit decreasing?
Negative 5.
At negative 5. When the x value is negative 5, it stops decreasing. And then at negative 5, it starts increasing until positive infinity. It increases forever.
Like mx plus b in like parentheses, x plus